Hey everybody, this is 2008 question 1, and it is a mathematical heavy one here. So let's get into it. Several students are riding in bumper cars at an amusement park. The combined mass of car A and its occupants is 250 kilograms. The combined mass of car B and its occupants is 200 kilograms. Car A is 15 meters away from car B and is moving to the right at 2 meters per second, as shown. When the driver decides to hit or bump into car B, which is at rest, so the initial velocity here is 0 meters per second. So they say car A accelerates at 1.5 meters per second squared to reach a speed of 5 meters per second and then continues at constant velocity. So calculate the total time of car A to travel the 15 meters. So this one is going to be kinematics. Now, how do you know it's kinematics and not energy and not momentum and not dynamics? Well, if they're giving you accelerations and velocities, initial and final, and distances, that's a key that it is kinematics. But it is tough still because it's a two-parter. Because anytime you have something where it's accelerating for part of it and constant speed in the other, you'll have to handle those two parts independently. So first, let's find the time it takes to go the acceleration part of it. So the first equation will be good for that. So the final velocity equals the initial velocity plus acceleration times time. So our final velocity is 5, our initial velocity is 2, our acceleration is 1.5. So 5 minus 2 is 3, 3 divided by 1.5 is 2. So it takes 2 seconds to go the initial accelerating portion. But when we go to the second portion, we need to know how far we need to go. So we also need to figure out how far we went. The third equation will be a good one for that. So the displacement will equal the initial velocity times time plus 1/2 times acceleration times time squared. So when we plug in for there, our initial velocity was 2, our time is 2, and then our acceleration, remember, is 1.5, and our time is 2 squared. So our displacement then will be 2 times 2 is 4, plus 2 squared is 4, times 1/2 is 2, times 1.5 is 3. So 4 plus 3 is 7. So we went 7 meters. So let's just say, around here we stopped accelerating. We went 7 meters there, which means we got to go 8 more meters at constant speed there. So now we can finally find our time. We know velocity equals our change in position over time. Our velocity, now that we're going at constant speed, is 5, and the distance we got to go is 8 meters, not 15. And so we got to solve for our time there. So time will equal 8 divided by 5, or 1.6 seconds. So 1.6 seconds for the constant speed part, 2 seconds for the accelerating part, there, and like that. So our total time then will be 3.6 seconds. That is a lot of math and a lot of different steps here to see what to do. All right, next part. This one's a little bit easier. It says after the collision, car B moves to the right with a speed of 4.8 meters per second. Calculate the speed of car A after the collision. Collision. Conservation of momentum is what you use there. So we know that the momentum of A before the collision has got to equal the momentum of A after the collision plus the momentum of B after the collision. So now let's start to plug in for what each of these would be. This would be the mass of A times the velocity of A before the collision has got to equal the mass of A times the velocity of A after the collision plus the mass of B times the velocity of B after the collision. And all of those but one are known, so we can start to plug in for those. Mass of A is 250 kilograms. The VA before is 5, not 2. So right before it hit, it was going 5 meters per second. The mass of A again is 250. We do not know how fast it was going afterwards. The mass of B is 200, and its speed afterwards, they told us, was 4.8. So let's solve for these two parts right here. 5 times 250 is 1250, and so that will equal 250 times our unknown speed, and then 200 times 4.8 is 960. And so now we'll have to subtract 960 from 1250, and we will get from that 290 is equal to 250 times our velocity of A afterwards. So now divide each side by 250 to solve for this, and then VA will equal from that 1.16 meters per second. Which way is it going? Well, this is a positive number. We've been using positive to the right, so this also is going to the right there. All right, last part here is whether or not it is an elastic collision. So a lot of people want to say it bounced, it's elastic, because they think of sticking together as inelastic. That's true, sticking together means it's definitely inelastic, but bouncing may or may not be elastic. What defines something as elastic is if the initial kinetic energy is equal to the final kinetic energy. So that's what we have to check. So the initial kinetic energy will be the kinetic energy of car A beforehand. And the final kinetic energy will be the kinetic energy of car A afterwards, plus the kinetic energy of car B afterwards. So we'll have to check both of those. So let's do this one. That's easy enough right here. We'll plug in for each of these numbers. So 1/2 times the mass of A is 250 times A's velocity before the collision is 5 again, remember, not 2. So if we work out that math, we'll get 3,125 joules of energy before the collision. Let's do this side here. What about afterwards? Let's just plug everything in. So 1/2 times the mass of A is 250, and the velocity of A afterwards is that 1.16 that we just solved for. So don't forget to square that, and then the kinetic energy of B will be 1/2 times its mass of 200 times what they said its velocity was after the collision, which was 4.8 squared. So if you work this out, you get 168.2 for this part, and you get 2,304 for this part. And so when you add those together, you get 2,472.2 joules. So we can see here that it lost energy. So that means it is inelastic. More specifically, you don't have to write this down, but it lost 652.8 joules of energy. Where did that energy go? Sound, heat, deforming the bumper cars. So because it lost energy, it is inelastic collision.